Okay guys, let's go ahead and talk about chapter 3, which is states of matter. The very first thing we're going to talk about is the kinetic theory, and we're going to learn the 3 assumptions of the kinetic theory. The kinetic theory assumes that all matter is composed of small particles. That means your pencil, the piece of paper you're writing on, the chair you're sitting in, that all matter is composed of small particles. It also assumes that these particles are in constant and random motion. Now, a bottle of water, we know that the water is also matter. It's composed of small particles, and it makes sense that those particles are in constant and random motion. But for the chair you're sitting in, that may not make sense, but we'll talk about that in a moment. The last assumption of the kinetic theory that we're going to learn is that these particles collide with each other and the walls of their containers. So just like a bottle of water we discussed a minute ago, the molecules of water are colliding with one another and they're colliding with the wall of that water bottle. Now the kinetic theory explains how we believe particles and matter behave. So let's go ahead and talk about the first state of matter, which is the solid. The solids are made up of particles and they're packed very close together in a specific type of geometric shape. So that's why the particles of your pencil are packed very close together and they're in a certain shape. And the reason you don't see them, the particles moving, is because they're packed so closely together that they just barely vibrate. And they're vibrating so slowly that you can't see them with your eye. Now let's discuss liquids, which is the next state of matter. This is when solids they liquefy at a melting point. And as they begin to liquefy, the particles gain enough energy to break apart from one another. So they overcome that ordered arrangement or that close packed togetherness that they had. Now, the heat of fusion is the energy required, or how much energy is required by that molecule to reach the melting point. And liquid particles, since they're overcoming their ordered arrangement, that means they have more space between them, allowing them to flow easier, and they can also change shapes. They can take the shape of their container. If you have a bottle of water, the water is in the shape of that bottle. If you pour the water out into a circular bowl, then it takes on the shape of the bowl, and that's what it's talking about here. Our third state of matter we're going to discuss is a gas. Now, in the gaseous state, a liquid's particles begin to have enough energy to also, again, escape the attractive forces of one another so that they can then break away and be even more free and even further apart. Now, the heat of vaporization is the energy required for one of those molecules to go from a liquid into a gas. At the boiling point of a liquid, the pressure of the liquid's vapor is equal to the pressure of the atmosphere, and so that liquid then becomes a gas. Okay? The last little bit about gas that we're going to talk about are that gas particles spread evenly throughout the container that they're in, and this is called diffusion. And it's just like if I have an air conditioning unit in my house, I don't have to have a vent every 2 feet, because wherever the vent is in that room, the air diffuses. Since it's a gas, the air diffuses throughout the room to help cool the entire room. And our last state of matter that we're going to discuss today is called plasma. And this we will not deal with very much because this is something that we do not see in our everyday lives as much. So we're going to deal with solids, liquids, and gases more in this class, but I do want you to know what plasma is. And this is a state of matter consisting of very high temperature gas, and it's balanced with positively and negatively charged particles. And I'm going to give you an example of what that would be in just a moment. Now, let's go ahead and fill out our chart that I have. Let's look at a solid. The shape of a solid is always definite. It doesn't change unless it's broken. And obviously, that's not what's supposed to happen to that solid. So the shape of a solid is definite. The volume of the solid is also definite. If you have a book, unless you saw off a corner of it, you're going to have the same volume. And sawing up the corner isn't how you're supposed to treat that book. So that's why we consider the volume being definite. An example would be like a block of wood, a book, your pencil, things of that nature. A liquid. Now, a liquid shape changes because depending on what container it is, it can take the shape of that container. The volume of the liquid, however, is definite. If I pour my water out of its water bottle into a circular bowl, I still have the same amount of water. So the volume is definite. An example of that is water, like we've been discussing. Now, the shape of a gas is going to change all the time to fit in whatever container it's in. The volume of air can also change, or of a gas can also change, and your example of that would be air. Now let's look at plasma. Plasma is actually the most common form of matter in the universe. It consists of free-moving ions, which you'll learn what ions are in a couple of chapters. But free-moving ions and electrons, it's very high energy. An example of this are stars and lightning bolts. They are made up of plasma. Now let's look at pictures to show you the molecular arrangement of these states of matter. The solid picture, as you can see, the particles are very closely packed together. They're still in motion, remember though. They're vibrating so slowly that we can't see them vibrating. And they're very tightly packed together. Now as you look at the liquid, you can see that they've lost a little bit of that ordered arrangement. They're able to break away from that ordered arrangement just a little bit to have a little bit more space. A gas is going to have the most space between its particles, and because it's completely overcome the ordered arrangement that it was in. Now what I would like us to do is look at a simulation about solids, liquids, and gases. Right here, it tells us over here that we actually have neon molecules. So these are neon molecules. And currently, it's in the solid state. Now, so these are tightly packed together molecules. I want you to make an observation. Here's the thermometer, and remember this K is for Kelvin, so it's at 13 Kelvin right now. And I would like you to, as we go from solid, liquid to gas, I want you to make sure you notice what happens with the thermometer. As we go to a liquid, they are able to break away a little bit from that ordered arrangement and have a little bit more space, but not as much space between the molecules as a gas would have. So we go from a solid, which they're vibrating so slowly that we're not going to be able to see them in a solid object, to a liquid where they have a little bit more space in between the particles and they move a little bit more, to a gas where they're moving very fast. Now, if you'll notice, at a gas, we're at 55 Kelvin for the temperature. We were at 26 Kelvin for liquid, and we're at 13 Kelvin for solid. What does that tell us? What is the relationship then between temperature and the energy of particles? Now, these particles have kinetic energy. That's what it's called, because kinetic energy is the energy of movement. So each particle has a certain amount of kinetic energy. So how is that related to temperature? And whenever we talk about what is the relationship between two things, it's just like if I said, what is the relationship between you and your brother? The relationship is that you're related and you're brother and sister, or brother and brother, right? So whenever I ask what is the relationship between temperature and kinetic energy, it means we have to tell how are they related to each other. So let's look at it in a different way. As I heat this up, what happens to the molecules? They start moving faster. So as I increase temperature, what happens to kinetic energy? It increases. As I decrease temperature, I'm decreasing the kinetic energy of the particles, and eventually they all slow back down. So let's watch that. So the relationship between kinetic energy and temperature is as you increase temperature, you increase kinetic energy. As you decrease temperature, you decrease kinetic energy. And that should make sense with our solid piece of ice, our liquid piece of water, and our water vapor. Because a solid piece of ice is very cold, right? It's got a very low temperature, and it's not moving very much. But when you heat up a piece of ice, the particles begin to move more and become liquefied. And then as you heat up the liquid water, the particles move even more and become water vapor. Now let's look at energy's role. Energy is the ability to change or to move matter. That's the definition. Energy allows matter to change from one phase to the other. So the fact that we're increasing energy allows ice to change to liquid water, or to go from a solid, liquid, and then to a gas. Because all of the particles in motion, all particles have kinetic energy, and that's what we just talked about in looking at that simulation. Now, temperature is a measure of kinetic energy, so it should be all coming together in your mind right about now. Temperature is a measure of kinetic energy, so as we increase temperature, we're increasing kinetic energy. And that's its relationship. Please be familiar with when someone asks you, what is the relationship between these two things? So as you increase temperature, you increase kinetic energy, but also as you decrease temperature, you're going to decrease kinetic energy. And this is called directly proportional. These are relationships that are directly proportional. It means that as one increases, the other increases. Whenever we say something is inversely proportional, that means as one increases, the other one decreases. So temperature and kinetic energy are directly proportional. They both, as one increases, the other increases. As one decreases, the other decreases. Now, thermal energy is the total kinetic energy of a substance's atoms. So however much energy we have, that's going to be the total of that energy is going to tell us how much thermal energy we have. Now let's talk about thermal expansion. The size of a substance will increase when the temperature increases. The size of the substance will decrease when the temperature decreases. This is why you see cracks in concrete sidewalks, because concrete expands and contracts. And so in the high heat of summer here in Valdosta, the concrete sidewalks have to have room to expand so that they don't crack. And so those cracks that you see every once in a while on the concrete sidewalks allow room for that expansion. Now in the winter, they're going to contract and they're going to get smaller. Expansion and contraction occur in most solids, liquids, and gases. And I'm going to tell you the one exception, and that exception is water. Because actually as water goes from liquid water to become a piece of ice, it expands as it becomes that solid. And so that's the only exception. Now we're going to touch on, real quick before we finish up, we're going to touch on the changes of state. So going from a solid, liquid to a gas. Now you have this chart. You do not have to worry about this deposition right here and the disorder of system. You don't have to worry about that. That was just in the picture, and it won't let me take those out, and so just don't worry about that. I've taken them out on your notes. But go ahead and fill in. You have one blank listed, I believe. Now, as you can see over here, this is giving us an arrow to show the energy of system. So as we go from a solid to a gas, we're increasing the energy, which should make sense because remember, when we increase temperature, we increase energy. Going from a solid, say piece of ice, to liquid water is called melting. And remember, we have the heat of fusion when we melt. And then going from liquid to a gas is called vaporization. Or you could put evaporation. We call it evaporation a lot, and that's perfectly fine. You can put evaporation. Then if we have a gas and we want to go back to a liquid, it's condensation. And condensation is the stuff that you find on the outside of your glass of iced tea. You know how it starts having water on the outside of the glass? It's because the air that is around that glass is all gas. And when that air touches the solid piece of glass and it's cold, it starts to condensate, because what you're doing is you're bringing down the temperature of that air. And as you bring down the temperature of the air, it's going to turn back into liquid water. So it condensates. Then if you want to take a liquid, like liquid water, back to a solid piece of ice, you're going to freeze it. Now, there is one change of state that you might have not heard of before, and that's going from a solid straight to a gas, and you skip the liquid phase, and that's called sublimation. And what you need to do is right underneath sublimation, write your example of dry ice. Most of you have probably seen dry ice, and we'll get to see some in class. But dry ice is a solid piece of ice, and it goes straight to gas. And so that is sublimation. One important thing we need to remember is the law of conservation of mass and energy. And anytime we mention law of conservation, that just means it's conserved. It means that it can't be created or destroyed. So mass can't ever be created or destroyed. Energy can't be created or destroyed. So when you're going through these changes of state, you're not losing mass, you're not losing energy, it's just changing to different forms. One example of this would be burning a piece of paper. If I burn a piece of paper, it looks like, and I only burn half of it, it looks like we've lost mass because that piece of paper would not have as much mass as we started with. However, the other mass that we think we lost actually can be measured in the smoke that was released and the ashes that were formed. And so you don't lose mass, you don't lose energy, they just change into other forms. All right, this concludes today's video. And what I need you to do is do a summary of what we've learned today. And I would like you to do this summary. I want you to write the letters D as in David, F as in Frank, H as in house, and L as in Lucy. Write those 4 letters. I want you to write a word or a phrase that describes things that we talked about today in our video. Have a great evening.